So this is kind of picking up partway through where we left off the notes at the beginning here. We have so far talked about the first derivative and the first derivative test. This, where we got to yesterday, is about the second derivative and the second derivative test. What we left off with yesterday was the notion that when the second derivative is equal to 0, you get a candidate for an inflection point. And let me kind of go back in and kind of re-highlight why that was true. The notion here was when we had this inflection point, this point of inflection, at that point, look what happens as you approach it. The slope of the line starts off like 0 down here, and then it gets a little more positive and a little more positive and a little more positive, and right at that point, that's the most positive slope. You have a maximum slope. So how do you maximize or minimize something? How do you find where a thing has a maximum? You set the derivative of that thing. But keep in mind what I said is it's getting bigger and bigger and bigger. What's getting maximized here is the slope. And the slope is the first derivative. So how do we maximize the first derivative? We take its derivative, which is the second derivative. So anywhere the second derivative is equal to 0, that's a candidate for an inflection point. Doesn't have to be, just like critical points aren't always max and mins. So this is what's going to happen then. When the second derivative is positive, we figured out yesterday that the graph of f is concave up. When the second derivative is negative, we figured out that the graph of f is, what did I just say? I don't think that made sense. Let me say that again. When the second derivative is positive, the graph is concave up. Is that what I said? Okay, good. When the second derivative is negative, the graph is going to be concave down. So for there to be a point of inflection, what has to happen with the second derivative? There must be a change in sign. Use the word change. So if I say, prove to me that there's a point of inflection at 5, you're going to first show me that f double prime of 5 is equal to 0, and then you're going to show me that to the left of 5, maybe you plug in 4, it, for example, might be less than 0, and to the right of it, it's greater than 0. So if you've shown me those two things, then you can say, since f double prime has a change in sign, and you can say it that way, use like squiggly writing with, there's got to be a change in sign at that point, then that 5 is a point of inflection.
So for the concavity,
yep.
So the graph f is just the original graph.
The original equation, right. Right. Second derivative test. Actually, before I tell you the second derivative test, I'm going to go back and I'm going to highlight about the first derivative test. Say I have a graph that does this, and here's the point A. Clearly from the picture, I can tell A is a maximum. The value at A is a maximum. First derivative test, you would have to show that f prime of A is equal to 0. And then you would have to show me, just for simplicity, let's put a number to this. Let's say that's 5. So then I would say f prime of 4, or pick any number to the left of that. F prime of 4 would be, in this case, greater than 0. F prime of 6, in this case, would be less than 0. And so the phrase you say, the first derivative, you have to know that the first derivative is equal to 0 at the point, and there must be a change in sign, thank you, of the first derivative. And so you say And literally you write the sentence using English words with math. Since f prime of 4 is less than 0, greater than 0, I can read. F prime of 4 is greater than 0, and f prime of 6 is less than 0, and f prime of 5 was equal to 0, there's a change in sign of the first derivative at 5. Therefore, 5 is a maximum. Because look what's happened. The first derivative changed from positive to negative. The function changed from increasing to decreasing. If the first derivative goes from positive to negative, that's got to be a max. Now, here's the advantage of the first derivative test. You only have to find one derivative. The disadvantage of the first derivative test is you've got to evaluate it at 2 points. I got to know that the first derivative goes from being positive to being negative and that there was a change in sign. So the hassle is you got to evaluate 2 points into it. Not that big a deal. Now, let's talk about the second derivative test. Look what the hypothesis is. Look what must be true. If f prime of c is equal to 0 and, key word there, and, both of these things must be true. Well, first of all, what does it mean when the second derivative is negative? What's going on with the graph? It's concave down. The function is concave down at that point. So if the first derivative is equal to 0, critical point, if the second derivative is negative, concave down, then you're going to get a picture that kind of sort of looks something like this. So if I have a horizontal tangent and the graph is concave down, that point must be a maximum. Similarly, if I have the first derivative equal to 0, but the second derivative positive, now the function is concave up. And so that point must be a min if it's concave up. Disadvantage of the second derivative test. Now, both of these tests prove the exact same thing. They both are designed to prove that a point is a maximum or that it's a minimum. So when it says, and justify your answer, what it's looking for is, what's your mathematical support that you've determined that this point is a maximum? So that you don't have to go check every infinite number of points nearby to find out that it is in fact bigger than all of them. So they both prove the same thing. You would never do both of them on the same problem unless it said, just for giggles and kicks, show me that you know how. It's not, you wouldn't do both. You'd pick one or the other because they're both showing if something's a max or if it's a min. So if I want to show that a point is in this case a minimum with the second derivative test, the disadvantage is I got to find the second derivative. So not just the first derivative, I got to go one step farther and find the second derivative. But here's the deal. Look what this says. Look how many points I have to plug in. Just one. I want to know whether the graph is concave up or down at that point. I don't need to check 2 points on either side. I just want to know what's going on right at that point. So the advantage of the second derivative test is you're only plugging one number in. So it's kind of a toss-up as to what's easier. Many of the problems want you to do a whole bunch of stuff. If you're finding increasing, decreasing, and you're finding stuff about concavity, then usually the second derivative test is easier because you've already had to find the second derivative. So, yes. Think it went away?
Yeah.
All right.
If we're going to use some test, we have to state that it's a second derivative test.
No.
Okay.
When you do this, you're in the second derivative. Yeah, Kate? So f double prime, so let's see. So if I got f prime of c is equal to 0, and it turned out that f double prime of c equals equal to 0, then you got something that looks like that. So when the second derivative is equal to 0, that's a potential point of inflection.
Okay.
So it's not a max or a min.
No.
So the first and second derivative tests are about showing that the point is a maximum or a minimum value. All right, let me take a deep breath there. Don't breathe that deeply. Too deep. All right, so watch this thing. This is not about proving a max or min. This little exercise, this example. This is just playing with everything we've learned. So one of the questions in the book is to find intervals of increasing and decreasing. Now I picked a super easy problem, not that one. I picked a super easy problem. We know what. Get back to the right spot. There it is. We know what that looks like, right? X cubed. So all I want to do, I picked an easy one where we knew the answers, so we could kind of see, okay, yeah, that makes sense. When the math says it's increasing here, yeah, I know it's increasing there. So it's kind of overkill. This is way overkill for this problem. But once we get these ideas down, then we can transfer that to more difficult stuff. So let's first talk about increasing, decreasing. Where's this graph increasing? Where's it decreasing? So increasing, decreasing comes from the first derivative. So I'm going to take the first derivative, see what we get. So if I want to find out where it's increasing, I would simply find out where is the first derivative greater than 0. Anywhere the first derivative is positive, the function is increasing. So derivative, right, 3 comes down, exponent smaller by 1. Set that equal to 0, wacka wacka. Don't forget, this is really a piecewise defined function. And so you get the positive version of that, you get the negative version of that. Now the thing I need to double check on for you guys is the endpoint thing. It's increasing when the derivative is positive. And so I want to double check, kind of verify it, because if I were looking at the graph, I would say, oh, it's increasing everywhere. But at that instant at 0, where you have the horizontal tangent, is that not considered increasing at that point? And let me kind of think on that and read better in the book. Well, I haven't done it yet, though. They did not include, but see, I don't think they would actually say.
They use a parenthesis.
Yeah, they use parentheses on that, but I can't imagine that it's not increasing on all real. So I wanted to read more into other stuff. So you're right. I kind of glanced at the book yesterday, but really I don't think I got a definitive answer.
What do you want us to do?
Right now, don't worry about it. Yeah.
Just do parentheses.
Yeah, just do parentheses. So yeah, that's fine. Right? So where is this function increasing? Well, it's increasing on that interval. It's increasing on that interval. Piece of cake. And we know that about x cubed, right? We know what the shape of x cubed is. That's first derivative. That's what it tells us. Second derivative tells us about concavity. So let's figure out where this thing is concave up. Concave up anywhere the second derivative is positive. So take the second derivative, find out where it's positive, any number is greater than 0. That's all the proof you need. If I say, show me where this graph is concave up, how do you know? I know because I've taken the second derivative and said it's greater than 0, and so find that interval. Now, if I did it as interval notation, zero to infinity. It's concave up.
That'd be the same as y prime.
Say again?
That'd be the same as y prime.
well, y prime increasing was also negative infinity to 0. Oh, where is y prime increasing? Yes.
That's what this is.
Yes. Yeah. And y prime is the slope. So where is the slope increasing? And so think about what this looks like, this graph. And so right here, y prime is 0 because it's a horizontal tangent. And then y prime gets bigger, bigger, bigger because y prime means slope. And now look here, the slope is really big number, but that's getting smaller, 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 smaller. It's getting closer and closer to 0. So here, the slope is decreasing. Here, the slope is increasing. And that's what this is saying. Here's the second derivative, which is the slope of the slope. The rate of change of the slope. This is, of course, concave up. If I wanted to show, and that's anywhere this second derivative is greater than 0. And if I wanted to show concave down, I just need to turn that thing around. Where is the second derivative less than 0?
It's not always
Right, this is increasing concave up. Here's a quick aside. Next time you go to Kings Island and you ride the Beast, they tore it down? Son of Beast is still around? The Beast was the big wooden one, right? Is it gone, really?
No, the beast is still there. The son of the beast is gone.
Well, it's not horrible.
It is
All right.
horrible.
All right, pick your roller coaster of choice. You get on the roller coaster, and it starts off, and it goes like this. First derivative is positive, and the second derivative is positive. So you got both the first and the second derivative positives. Now you can't stay that way forever, because if you did, you'd loop back over and you'd fall out because you don't have enough speed. So we can't keep doing that. So at some point, I need to change to this. So now the first derivative is positive, and the second derivative is negative. And once you get to the top, you start down the hill. And we go down, down, down. And of course, at that point, the first derivative is, and the second derivative is negative. Now you can't keep going down like that, because it puts a damper on your whole day when you smash headlong into the ground. So we need to stop going down, 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 and turn a little bit. Let me slide over. And turn a little bit and come this way. So now I got first derivative, negative, and second derivative, positive. So you go through all four of those. Now, literally, people who design roller coasters look at those kinds of things. And at the point where these guys join, the slope of the tangent on the green one and the slope of the tangent on the blue one have to be identical. You can't have that change and have it go, make a jerk to a different slope. It has to be a continuous flow on these connecting graphs. And so as they design it, those are the kinds of things they look at. So that the ride needs to be smooth enough that it doesn't cause the car to jump off and everybody die, which occasionally happens.
Occasionally happens.
Yeah, didn't you hear about that kid who got decapitated on a ride last year? Literally decapitated, like his head got chopped off.
What happened? Wait,
Yeah.
where was he?
At the State Fair, wasn't it State Fair?
Yeah.
Oh my gosh.
Yeah, not a good day for him. All right, so we just did this. Draw me a quick curve.
Is this just like a simple line?
Should look like that. Make sense? First derivative negative means it's going down. Second derivative positive means it's going down in a concave up manner. All right, let's do one of these together. I think this is number 9 from the homework. You got a book out by any chance?
I think it's true. What page is it?
4.3.
Yeah, this is
229.
9 is fine. It's f of x
Give me the equation.
equals 2x cubed plus 3x squared minus 36x.
Okay. And so they want us to find a whole bunch of stuff. Now, we know stuff about that shape. We know what cubics look like. But the first question is about increasing, decreasing. Now, the first derivative doesn't tell you max or mins. Listen to the statement. The first derivative doesn't tell you max or mins. It tells you about increasing, decreasing. And then from increasing, decreasing, I can determine if the graph was increasing followed by decreasing. John? Then I know that point's a max. Hey. Got a bio book over here? Let's see. So first derivative, increasing, decreasing. Second derivative does not tell you about points of inflection. It tells you about concavity. And from the concavity, we can determine points of inflection. All right, so the first one in here says part A, tell us about increasing, decreasing. So to do that, I'm going to take this equation, and I'm going to find a derivative. Now, I will dock you if you do not appropriately label stuff. Some of you hate doing that. I'm telling you now, you're going to lose points. Don't just have the second derivative hanging naked out there in the world. Put some clothes on it. Tell me what it is. So f prime of x equals 6x squared plus 6x minus 36. In order to find increasing and decreasing, I need to substitute in various values. But instead of just randomly picking some, let's see if I can figure out where the max and mins occur by figuring out where that equals 0. Now, the question really wasn't about max and mins, but there's a relationship. Here's the thing I notice. They all got 6s in them. So, here's what I know at -3 and at 2. Something's going on. Now, without doing any calculus, well, I did one step in calculus already, but without doing any more calculus, because I know what this shape looks like, I know this graph goes up, has a maximum at -3, a minimum at 2, and zigs back up. I know that. So I don't, to get the answer, I don't need to do that. The point of this problem is an easy problem to figure out the calculus and what you need to do as the problems get harder. So when you have something like e to the square root of the sine of x. Yes. You can still do the logic and know what the logic is. So now that I've got those 2 points, if I want to find increasing and decreasing, so let's do it this way. Let's prove that there's a maximum at -3 using the first derivative test. So to prove there's a max at -3, I need to take the derivative and ensure that it actually equals 0 at -3, because that's the first derivative test. Now, I already did that, right? This is proving that I should go to the next step. X equals -3 and 2. So here I've shown you that the first derivative is equal to 0. So that would be part of the hypothesis of what you have to show to use the first derivative test. Have you shown me the first derivative is equal to 0 at that point?
Can you say, since we know that it's a positive cube, that it has the max on the left and the...
Yeah, no. I can, but no. No, that's what I was just saying. When you get problems where you don't know that, this is the logic of what you have to show. So I got to show that the derivative is equal to 0 at that point. Then I need to show first derivative test that f prime of, for example, -4. Pick any point to the left. Be nice to yourself. You could put in -3.0001 if you want, but that's a little bit of a pain. And you need to evaluate. I got to go back here and get the equation. I need to evaluate this function at, that's f prime, right? I need to evaluate that function at -4. So when I plug -4 into there, that's going to be 16 times 6, that's 96. That's going to be negative, but that's still greater than 0. So what I've just shown is that to the left of -3, f is increasing. There's not going to be any place else where it suddenly changes to decreasing over there to the left of -3. But what?
I was going to say, could you test f prime of -2?
Then I'm going to say f prime of well, I'm even going to make it easier. F prime of 0. F prime of 0, well, 0, 0, -36 is less than 0. So what that tells me is f is decreasing from -3 to 2. Because at -2, it's 0.
So,
Oh, I'm sorry, at +2, it's 0. At -3, it's 0. At +2, it's 0. And it's negative in between. So it's decreasing everywhere in between. There's no other zeros in there, so it can't zigzag mysteriously in the middle, unbeknownst to me. Yes, sir.
Last year, instead of saying this, we drew a number line. We put like a plus sign on the top of like.
And I'm gonna we'll
arrow.
get to the save that.
Can we say that instead of saying this and conclude the same information from that, or do you want us to write this out?
Not yet. Yeah, save that for a little bit. So far, so good. You see what I've done? And all I'm doing, the only thing that the number line is doing is it's kind of bypassing the acknowledgement that I've plugged a number in and found out that it's negative. So all I'm doing is just writing the words that it's decreasing on that. Yeah. So it's not really doing anything. So then what I'm going to do is I'm going to find f prime of 3. Why am I picking 3? Because it's greater than 2. Any number to the right of 2. And so when I plug 3 into that, that's going to end up becoming greater than 0. And so, greater than 0. So what that shows then is that, f is increasing on 2 to infinity. That's a comma. Now, I haven't done the first derivative test yet. I've taken lots of first derivatives, but the first derivative test is to show whether a point is a max or a min. So, in an English sentence, you would write some sort of conclusion at the bottom. Since f prime changes signs from positive to negative at -3. This is the English sentence you write, the whole sentence. Since f prime changes from positive to negative at -3, then -3 is a maximum. Now you could say, no, say that. Because it's about the change in the sign of the first derivative. Then in a second sentence, you could say, since f prime changes from negative to positive at 2, Well, if the first derivative changes from negative to positive, the function changes from decreasing to increasing. Therefore, x equals 2 is a min. Make sense? Yes, sir.
So you want us to write more than just therefore x equals 2?
Yeah, I want this. I just ran out of room here. I want that sentence.
Okay, yeah.
I want the acknowledgement that you understand that what has to happen for the first derivative test to work is there has to be a change in sign of the first derivative. So I want you to write the words because there's a change in sign of the first derivative at x equals. Therefore, that's a.
So you said you found that the f prime of 3 is greater than 0. Don't you have to find like f prime of 1?
No, because you had negative 3 and you had 2. So 0 takes care of any number in between. It doesn't have to be smack dab next to it. Anything on the interval. I'm going to do the exact same thing I just did, but now I'm going to use the second derivative test. This is overkill. I don't need to do this twice. You would pick one or the other. You wouldn't do it twice. The first derivative was that 6x number thing, right? So I think I have that copied still. Yeah, there it is. So that was the first derivative. And so the second derivative is of x is 12x plus 6. So here's what the second derivative test said. Look at your notes that we just wrote down today. If the first derivative is equal to 0 at a point, and we found that to be true twice, specifically negative 3 and positive 2. And then it said, if the second derivative at that point, I don't need to check points on either side, I want to know what's going on at that point. So now I want to check f double prime of negative 3. So if the second derivative at negative 3 is negative, what's that tell you about f? F is concave down. So if the first derivative is 0, which means I have a horizontal tangent, and the graph is concave down, if the first derivative is 0, and the graph is concave down, that point is a max. This is enough, using the second derivative, to show that the point at negative 3 is a maximum. Therefore, f of negative 3 is a maximum. Now, if the question said what's the maximum value, then I got to go back and find f of negative 3. Plug it into the original equation to find the y value. Not yet. I'm getting there. So what I'm working on still is proving that these 2 points are maximums and minimums. Same logic's going to hold true if I want to show that at 2 there's a minimum. I'm going to find f double prime of 2. Now I've already verified that this is equal to 0 at 2. I already did that. So since the first derivative is equal to 0 at 2, and f double prime of 2, well, plug 2 into this. So 24 plus 6, that's greater than 0. What's going on the function at 2? The function's concave up. It's concave up, and there's a critical point. Therefore, that critical point's got to be a min. Say again?
You just solved what we just did.
Right, I just double whammy. Same thing twice. This is just an alternate way of doing it. The advantage of the second derivative is I only had to plug in 1 point. The disadvantage is I had to find the second derivative, but in this case, I mean, that wasn't hard. Sometimes, like when you have those e to the square roots of sine x, they are a little trickier to mess with. Now, different question, new question. Let's find the point of inflection, if there is one. Points of inflection occur when the second derivative is equal to 0. We found that the second derivative was 12x plus 6. Set it equal to 0, 1/2. Is that enough information to say that 1/2 is where the point of inflection is? What do I need to show? There's got to be a change in sign of the second derivative. So, I'm going to need to, let's, say again? Second derivative. Because the concavity has to change. Second derivative is concavity. The concavity has to go from up to down or down to up. So second derivative, let's try -1. Plug -1 into that. I got -12 plus 6. That's less than 0. So therefore, f is concave down.
So what you're doing now is just plugging in points on the side of the zero.
Yes. So I'm not proving max min. I'm proving concavity. I'm proving there's a change in concavity. But on either side of the 1/2 number, -1/2. So now I'm going to do 0, and plugging in 0 gets me 0 plus 6, which is greater than 0. Therefore, f is concave up. And now here's your concluding sentence in English. Because f double prime changes signs from, well, you don't even need to say from, just the fact that it changes signs, then f has a point of inflection at x equals -2. Because f double prime changed signs, has a change in signs at x equals -1/2, then f, original function, has a point of inflection at that point. Or you could say x equals -1/2 is a point of inflection. Yes, the original function is a point of inflection at that spot. Like this? Yeah. Yeah. No. So, yeah.
So, you find the place where it could be a point of inflection, and then you find the concave down, and then you prove that it's.
And then the conclude. So what must be true for there to be a point of inflection? This has got to equal 0. Show that. And then there has to be a change in sign. So I picked points on either side to show that one side was, the second derivative was positive, the other side the second derivative is negative. So that means there's a change in concavity.
So you're just like proving the two things that make the conclusion true.
So let me show you something here. This original graph was a cubic. At -3, I had a max. At 2, I had a min. So ballparkish, this graph looks something like that, right? Now that's f. So let me draw the derivative of f. Well, the derivative of f is equal to 0 here and at here. So there and there. Now, what did we show to the left of that -3? We showed that the function was increasing. The derivative was positive. So f prime is going to be positive over here. Now, at this point, what kind of slopes do I start getting? Okay, so when I'm graphing the derivative, listen to this phrase. The y values of the derivative are the slopes of the function. The y values, look, these are y values. The y values of the derivative are the slopes of the function. Right? Because everywhere between those numbers, the slopes of the blue graph is negative. Therefore, the y values of the red graph, the derivative, should be negative. To the right of 2, the slopes are positive. Therefore, the y value should be positive. Let's look at f double prime. Now, what that really means is I just need to take the derivative of the derivative. So ignore the blue graph for a minute and look at the red graph. Where does the red graph have a minimum? As it turns out, -1/2. So even though my graph is kind of a rough sketch, right, we found that to be true. -1/2 is where it actually occurred. Over here, what are the slopes of the red graph? Therefore, the y values of my graph will be negative. Now, remember how derivatives work. When I start with an x to the third power and I take its derivative, I get an x to the second power. When I take the derivative of an x to the second, I get an x to the first power. It's just a line. Now look at something. Look at the black line at this point. That's the second derivative. The second derivative is positive at this point. So what does that tell you about the function at that point? It's concave up. And so sure enough, at that point in there, this graph is concave up. What does this point being positive tell you about the first derivative? The slopes are positive. So from this point, look at the red graph, I've got positive slopes right there. Look at the black line. Everywhere to the left, this black line has negative values, which means on the function, everywhere to the left of that point, this is going to be concave down. Black line to the right of that point. Everywhere to the right of that point, I've got positive y values, which means the function's going to be concave up in that area. Yes, sir?
So what would the third derivative be?
It would be a horizontal line at whatever that slope is.
Okay.
Because there's no zeros to it, so there's no max or mins on that black line. And it's a constant slope of whatever that slope is.
Would it know like inflection of the first derivative?
But as you can see, the first derivative, the red curve, doesn't have an inflection point. And so that would be the third derivative of the original function is the second derivative of the derivative. And the red curve doesn't have an inflection point. And I think this is, if I'm remembering right, this would be, it was 12x, so the slope of that line is just 12. So the slope of this black line is 12. And so it would just be a horizontal line up here at 12. So where does that black line, horizontal line, cross the x-axis? Nowhere. So where is this function going to have a max or min? Or an inflection point? Nothing.
Do you ever deal with figure?
Not so much. So
What would they be?
But if that was,
it's, go ahead.
say your function, your blue line was actually f prime, so add like a prime to each one, and then you drew that extra line. So that would add to f prime.
Yeah, but that doesn't change this relationship between these three.
But that would be the slope, or that would be the inflection point of the rate.
So that's just, that means the first function, that means the first function would be, so look, negative slope, this is negative slope, positive slope, negative slope, positive slope. That's a fourth degree polynomial. It's a W-ish thing. Yeah. All right. That's where we're going to go with this. And there's, in one hand, it's not hard. But now what we're doing, we spent all this time figuring out how do you take derivatives, but now we're putting some meaning to it. And that's the way we teach math a lot, where we learn kind of the grunt work of stuff, and then we layer on some understanding behind why we did all of those things. So, check Blackboard for homework.